Hello everyone, thanks for tuning in. Here on the benchtop I have assorted electrical and mechanical components removed from a treadmill that I featured in a previous video. I removed these components for clarity and for show and tell for this video. One of the defective components on the treadmill is its belt speed sensor. It's quite important. Your treadmill will likely to have one like this. In this video I'm going to feature this belt speed sensor, how you can go about replacing it as part, and what's involved in its replacement and installation. I'm also going to explain a little bit about how it works, because its operating principles drive its installation conditions. So the replaced part doesn't get damaged the same way from the rotating components, the same way as the first one did in the first place. So, with all that on the menu, we're gonna get started, but this video is not a tutorial, this is not advice, and is not a lesson. This is a show and tell. I'm not telling you what you should or shouldn't do. You do the thinking for yourself on your own. I'm telling you what's involved. That's it. So, let's get started. The damage on this speed sensor is only cosmetic, superficial, and this speed sensor is fully functional. The speed sensor itself looks like this black cylindrical object that has some gouge marks. There shouldn't be any gouge marks on it, and especially there shouldn't be one side of it abraded flat at one point like this. That shouldn't be on it. However, this amount of damage does not stop this sensor from being fully functional. It will remain functional even if it's abraded even more. When it is abraded even more, you'll see that inside there is a coil of wires. Those coil of wires could be exposed and will remain to be fully functional unless one of the wires are broken on this coil, at which point this is going to stop functioning. Underneath the coil of wires there can be nothing, an air core, or there could be an iron core underneath this coil of wires. So either air core or iron core, either which way, this is what's inside. There are no moving components inside. This is what's meant by this is a solid state device. I'm going to go through different terminology for parts replacement, and sometimes how it's listed could be solid state is one word that's being mentioned. So that's what's meant. There are no moving components inside. However, it's placed in the vicinity of moving components: motor, pulley, belt, flywheel, whatever. And those moving components did this abrasion or this damage. Now, in order to access this machine, of this sensor on the machine, you don't have to take apart the machine like this is. All of these components are underneath the machine, inside the frame of it. So the motor drives the pulley drives the belt, the motor drives the flywheel drives the belt drives the pulley, and in the middle of the pulley a roller runs through it, and on this roller the track is stretched. You're doing your steps, running, jogging, whatever, on this track. So the rotating components, the track itself, the roller, the pulley, the belt, the flywheel, all of these rotate and vibrate. So however this wire is placed on the frame of the machine in the neighborhood of these components, it can get entangled, it can get torn, this sensor can be shredded. So all of these, it's not possible to place it really any other place. It has to be kind of underneath the machine. And to access this part, it plugs into the circuit board. I'll show you how, but it's fairly straightforward because it's at the edge of the frame here around these rotating components, because this is the end of the roller at the edge of the machine. So it's somewhere on one side or the other of the machine. So to access it, all you need to do is flip the machine up. All you need to do is unplug the machine and disconnect it to make sure everything is unenergized, because this is an electrical equipment. And then wait, I don't know, half a minute so the charges dissipate. And then you flip up the machine on its side, and then you can see this wire running somewhere taped or held in place by, I'll show you these clips that hold this wire or held this wire originally. So it's somewhere on the edge of the machine at the end of the roller that drives the track. The track is the big wide thing that you're running on. So I hope that makes sense. So you don't have to remove any of this stuff from the machine. You just have to find the wire if it's damaged. The wire itself, so let me just show you, it's fairly straightforward and is held in place by these clips. Here is one such clip, and it detaches like so, fairly straightforward. This clip itself is self-adhesive normally, and I just tore it off from the machine's frame, so it's held in place like so. And if you put the new wire with the new sensor in there, it's gonna stay in place kinda. It's been working pretty well for this particular machine, although you can see what happened. So it did get damaged there. So this is one solution for keeping the wire in place. You can also tape it with electrical tape or duct tape or packing tape or whatever tape. Tape this wire to the frame to keep it in place, or tape this sensor itself to the frame to keep it in place. However, placement is critical, and I'm going to explain some other options as we go along. So this clip is one option. As you can see, the wire is fairly thin. This type of wire is used in speaker wires, as in earbuds and earphones, something like that. But just for contrast, here is this other wire here. It says 600 volts on it right here, so it's a much heavier gauge wire, and this is whatever the supply voltage in your country and your market, that's what's going to run through it. 240, 220, 120, 110, whatever. So this is super skinny wire, and its size is 24 gauge. Let me just get you a nice spot on it where it says 24 gauge there, and it's 24 gauge AWG. Let's see, getting there, right there, 24 AWG. I know it's difficult to read, but that's what's printed on it. So American wire gauge 24. So very skinny wire. Let's get back to, for one sentence, to the fact that this is solid state. So how does this work? And how did this get damaged? Of course, it's close to these rotating items such as this flywheel. And how this works is, inside the flywheel there's a piece of magnet, which you can see here. This sensor is close to the magnet, and by close it means about this close there, 3 millimeters, maybe 5 millimeters. So that's 1/4 inch, an 1/8 of an inch, something like that. They shouldn't be touching, but they should be close, either the side of the sensor or the end of the sensor, like so, should be close to this rotating magnet. This rotating magnet is going to be replaced for now with this magnet that I have. It really is a magnet. It sticks to the flywheel, strong magnet, because it's easier to handle it for the video. So as the magnet on this flywheel passes by this coil of wires here, which is the sensor, the wire itself is made of a metal, maybe copper if it's a cheap sensor, maybe some other alloys of exotic metals. So this magnet passing by, the magnetic field on the magnet is able to rip out some of the electrons on the copper, on the conductor, on the wire, on the coils, and is able to move the electrons up the wire. This magnetic force moves some of the electrons. That means that this generates a little bit of electricity. How much electricity are we talking? We're talking millivolts and a very, very low current. This is just a single pulse that it generates, just one blip, just that, and then nothing. And then it turns around again, next time around, just one blip, nothing else. So that signal is an indication for for your console that I don't have here, or your your dashboard, that the belt itself is indeed rotating. So it's a feedback or control mechanism. Okay, so magnetic field, move some electrons, it generates one very low voltage signal on that moves along on this wire. The wire continues in this connector. The connector itself comes apart like so, so you can take out this piece, disconnect it from its clip, disconnect it from the machine. That's where you find it, along the frame, somewhere along this pulley that drives your track, and that's it. Your best option for replacing this part is get an identical one from the manufacturer. Now this one is unmarked, unidentified, so what manufacturer? At this point you're kind of running out of options, because for manufacturer all you have is your Treadmill's manufacturer, and they may not have this in stock. They may have this as part of the whole electrical harness assembly, part of the harness, and is not being available for just this much. This costs about $10. Good speed sensors could cost $1,500, but this one is a $10 item or some such thing. So if your manufacturer can't give you one, or won't give you one, I don't know, what are your options? We're going to go to this catalog. This represents one electrical supplier, so you're going to have to find an electronics parts supplier, and in it you'll find speed sensors under different names. I'm going to explain these names. That's why I said this is a solid state speed sensor. So solid state is one of the words that's going to show up in the catalogs. So we'll get there. Just one more thing. So because the magnetic field moves some electrons in the wire, therefore this is very low voltage, very low amperage wire, and a very skinny 24 wire gauge. That also means that these points are not a potential for electrocution, or not electrical hazard. Even if the wire coils are exposed here, are not a source of electrical hazard whatsoever because of the extremely low voltage. So if the wire is torn, it can be safely just twisted back together and left out there for the elements, or okay, maybe for due diligence, why not put some electrical tape on it. The wire can be repaired if it's torn with just electrical tape and twisting it together. That's it. It will be a point of weakness in terms of the few millivolts coming from the sensor trying to go through a choke point that's mangled, and if you try to splice it back together by twisting the wires together, this signal may never make it to the circuit board or your dashboard or control panel, whatever, but it might work. I'm just telling you these are some options. Replacing the wire is easy. If you don't find these connectors somewhere, you might want to save these connectors, these white plastic connectors, but if you can't find them, again, an electronics parts supplier will have both wire, will have these clips and other clips and these terminals as well. Let me just show you one more thing inside the terminal. The wire itself, your replacement sensor may not come with this kind of connector on it. You may need to take it apart. The metal fittings inside that go on the end of the insulated wire, or somewhat like this metal fitting here for this ground screw, it goes at the end of the wire and is held together with some kind of friction method, some kind of crimping, or same principle. Okay, this one is fully insulated, but you can see a metal fitting fitted to the end of this wire. So in terms of metal fittings, you have the same idea there. Those fittings that you see exposed there are crimped to the end of the wire, and both fittings are plugged into this white socket. So this white socket you might want to save. You might have to crimp those metal fittings on to provide this connection, or you might want to just eliminate this and just twist the wires together. That's again an option for connecting a speed sensor to the circuit board. On the circuit board itself, these are all high voltage connections here, except this one. This is a low voltage connection with this skinny wire. This is where the skinny wire leads to. Let me just put the camera somewhere where you can see the action here. Try to pull on the connector only and not on the wire, because the wires with the metal fittings will rip out from the connector. So there you have the same idea there. The male connector is soldered in place into the circuit board. So that's that, and it's already loose. So, but anyhow, so that's what's involved. I'm just telling you the story. That's what's involved. Those are some options. Now let's see some other options for replacement of the sensor if the manufacturer won't give you one or can't give you one. What are some of your options? I couldn't find a perfect match in this particular catalog because we don't have the specifications of the original sensor. We don't know its output. It's kind of important to know its output because we need to match it so your circuit board can process the strength of signal this produces and is meaningful for your dashboard for display. But your options include, and I'm just showing you some options here. This is a completely different shape, but just for terminology wise, look at it. Solid state, yeah, so that's meaningful. Speed sensor. Now whether it's an ABS wheel speed or in a transmission like their anti-lock braking system, obviously automotive use with multiple pins on it for connecting, but a feature I want to focus on is it has an eyelet on it for a bolt to go through to ensure that this sensor does not move next to an automotive wheel. The same thing that could work, these sensors are available in different configurations, and one way of securing the sensor is to run it through a bracket. A bracket, not necessarily this one, it could be an ugly, it could be a nice bracket, not this ugly bracket, and appropriately sized because this is huge, but it's easy to film. So through it a hole can be drilled because these sensors come with smooth outside as well as threaded outside with lock rings on it. Here below there's one that's threaded. For this purpose you can see the two wires, two pins on it. It says same idea, solid state speed sensor. You get the idea. So the lock rings are over here, there in these pictures. Now these say proximity sensors, not speed sensors. It's the same idea, and it says inductive. I forgot to mention that word. This magnetic field force induces an electric current that goes up the wire, so this is an inductive magnetic sensor. So all of these words, although not interchangeable, but the product can be described with a number of these words. So proximity sensor or inductive sensor, it's all the same thing. Just make sure it's not a Hall effect sensor. It has to be inductive or magnetic. So you can see some of these lock rings, you get the idea. They work with a bracket. This is, I don't know, something from house building, so it's completely irrelevant to machines usually. And here is the same one, the threaded. Here is another automotive, maybe the same. Here is another variant on it. Probably lock rings I can see on the outside of it. And they all have their electrical specifications that I'm going to show you on some printed pages over there. Right here you only have its sensing range listed or its size listed, how big of a hole you need in a connector. This sensing range is going to be important, and holding this sensor in place, because this not being held in place well enough is what damaged this one, and yours could be, like I said, shredded to pieces. So that's why a bracket that's next to this rotating magnet somehow on the frame of your machine, and through a bracket, an appropriate sized hole, lock rings, whatever, you kind of get the idea. It doesn't need to be over explained, I think. So, but even so, the question of electrical suitability in terms of signal strength and everything, that's up to experimentation. But for what's involved in terms of securing the sensor to the frame, so here are some options. On a bicycle here, this is why I have a bicycle here, you can see how this is installed in a functional order. On the spoke here is a magnet. Over here is this proximity sensor or speed sensor, either which way, and it has no moving components. As the wheel turns around, at this point you can see there is a gap between the two of them. The magnetic field force on the magnet moves some electrons on the coil inside the sensor, very cheap $10 sensor, and those electrons are moving up this wire here inside this wire mounted on the frame, and eventually it makes its way up here to this cradle, there, to these two terminal points where electrical connection is made, and then these few millivolts get amplified inside this speedometer. That's why it needs a big battery. So the sensor itself is not powered, but the signal is so weak that it needs to be amplified. This distance of air gap between the two of them need to be carefully worked out. You can see right now we have between 3 to 5 millimeters of gap, and this works this way. This is how it was designed. Now if you move the magnet further down on the spokes, of course it's going to be misaligned, but if you move, and nothing is going to work. But if you move both of them further down, you'll see that the spokes are kind of getting closer and closer and closer to the frame or the fork of the machine. So at one point the sensor and the magnet are going to make contact with each other, and one is going to hit the other. That shouldn't happen. There always should be an air gap between the two of them. Okay, that's how the magnetic field force induces this electrical signal. So air gaps are important. Over here I have the same device, bicycle speedometer with a cradle with the wire on it, and this is its wire coil. This is its speed sensor. Here is my magnet, and if I whoosh the magnet or the sensor over the magnet, you can see that bicycle speed is indicated on the device. I'm doing 30 kilometers an hour, whatever, you get the idea. So there has to be an air gap between the two of them, and that is important. The size of this air gap can be specified by the manufacturer. This one is high output, fancy. All of them are threaded. Okay, yeah, all of them seem to, okay, that one is smooth, but most of them are threaded, so they can be kept in place. And you can see on the application details here, RPM this, RPM that, motor speed, speed, and whether it's wheel speed or belt speed, it's the same principle. And you can see for different designs they have completely different parameters, mechanical and electrical, and you can see the air gap here specified 5/1000th of an inch or 0.127 millimeters. So that's a little more than 1/10 of a millimeter. That's a finicky, tight fit. This one, the bicycle speed sensor, it works with a 3 to 5 millimeter gap. Same for this one, it works with a really generous gap, but again keeping the vibrating sensor end out of the path of the magnet or the belt or the track or something is going to be a challenge in installation. Again, It has no moving parts inside, simple installation, self-powered or not powered. And over here from yet another manufacturer you can see the same designs. So the outside of the sensor can be physically appearing either which way. It's the same sensor. Oh, instead of sensor they call it pickup, and it's magnetic of course. And again, it's self-generating, no external power needed, no maintenance whatever, encapsulated. I just want to show you this here in the bottom of the page. They also have an air gap of 5/1000th of an inch, so the same tight fit. And you can see it works with gear teeth, or bigger gear teeth, or cam lobes, or that's a keyway in a shaft. The keyway, here is a keyway in a shaft. Let me just pull this flywheel off. Everything is just fitted here for show and tell. There, that's just a cut in the shaft. That's a keyway, and that's what's represented here by this image. So any kind of rotating objects, that's a cam. So what you see here in the graph is that this rotating magnet over this coil produces a signal, a pulsating one single pulse as it passes through. That's it. That one pulse of electricity is what you hear, what you see here as signal output from this wheel speed sensor or belt speed sensor or just a speed sensor, whatever. Over here you can see the air gap specs. So 5/1000th of an inch is standard. It can be twice, 3, 4, 4 times of that. It can be more than that. But as the magnetic field is further away from the coils, fewer electrons will be moved in the coil. So that's what this graph is representing, that the amount of electricity it generates is decreasing with this distance here increasing. So try to get this sensor as close as possible. Okay, not as close as possible. Like a safe 3 to 5 millimeter gap is nice. If it's too close, it will still work, but it is likely to catch. If it's too far away, then the magnetic force in the magnet is not going to be moving any electrons in this sensor. So that's basically what I wanted to share with you. I know it's not a perfect solution for replacing the sensor itself. The best option is getting one from the manufacturer if they have one. If they don't, you're gonna have to tinker with it and play with it, and installation is gonna be critical. Thank you very much for